So we talk about reaction balance equations. I'm sure you can do that. You need to be able to balance the equation. Then we talk about the conservation of energy, a couple different ways of writing the conservation of energy for combustion system. We could have the Q dot into the combustion chamber or control volume divided by the molar flow rate of the fuel. Often we don't have any shaft power out, but the textbook writes it like that. So if you did, you could include it in the energy balance. Then we have the sum over all the products, the stoichiometric coefficient times the enthalpy of formation plus the enthalpy, the molar enthalpy at the temperature that the products exit minus the reference temperature, molar enthalpy at the reference temperature. That would be summed over all of the products. So that'd be like over all of the exiting products. And then you have minus the sum over all the reactants. Put an R down here. Stoichiometric coefficient, enthalpy formation, the molar enthalpy at the temperature that they're incoming reactants minus the molar enthalpy, the temperature reference. That reference temperature was 25 C, 298 Kelvin. When you have, almost always that term is zero, but if it's an adiabatic flame temperature, it's adiabatic, hence Q dot divided by N dot F is 0. And then you find the temperature exit such that the energy balance is 0 on the left-hand side. Okay? All right. Then we talk about the absolute entropy and the third law of thermodynamics, and we use that to write the second law. And so if you want, you can express the second law of thermodynamics as the rate of entropy production inside a control volume per molar flow rate of the fuel is equal to, then we have a minus Q dot divided by N dot F. This is the same in the energy balance. And you have entropy transfer with heat transfer, and the way you do it is you divide by TB. What is TB? The boundary temperature across which that heat is being transferred into or out of the control volume. As we've shown it, Q dot's into the control volume. The way it's written, that's why there's a negative sign in front of that term. Okay, what happens if the temperature of the boundary is changing and some heat is transferred at lower temperature and then some heat at higher temperature and some heat at a different temperature? We have to do an integration and it's nasty. Okay? But it's doable. But we just don't solve many problems like that. In this textbook, primarily at the boundary temperature, some average value, here it is, solve the problem at hand. All right, then we're going to have the sum over all the products, the same stoichiometric coefficient, and then what we have is we have this molar absolute entropy, which is a function only of temperature, so it's only a function T exit for the product, minus, because we deal with ideal gases, so this is an expression of the entropy for an ideal gas of the product going out, R bar, natural log, yi P exit over P ref. Often, P exit equal to P reference, which is 1 atmosphere. So it just becomes a natural log of Y. Okay. And then this is a closed parent right there. Then we have minus the sum over all the products, stoichiometric coefficient, absolute entropy as a function of temperature. That's the incoming temperature of each reactant, minus R bar, natural log, yi P inlet divided by P reference. And close, often you can just continue this. The exit pressure is equal to the inlet pressure is equal to atmospheric pressure. Often, that's often the case. Yeah, we need a R there for reactants, right? Thank you very much. Any other corrections to this? Does it look okay? All right. Okay, press forward. We have this problem. I solved it at the 9 o'clock. I may splice it in, make a longer video, or I may put it out as a separate standalone video. But I wanted to solve this problem. It's a very similar problem, but we'll solve this problem. So we have gaseous carbon monoxide at 25 C 1 atm enters an insulated reactor operating at steady state and reacts completely with 145% theoretical amount of air entering in a separate stream at 25 C and 1 atm. So you have two streams coming in. That's important. So you have the fuel, which is CO, and then you have air, and reacts and comes out. It's going to come out completely combusted. The air is 145% theoretical air. It's a what type of reactor? Insulated. Q dot equal to 0. It's operating steady state. All the inlets, I'm not going to repeat them, are 25 C 1 atm, 25 C 1 atm. The products of combustion go out at 1 atm. Obtain a balanced reaction equation. So can you obtain that reaction equation? Should I give you a second to do it on your own? I think I've done it a number of times. Let me just do it in the interest of time for you, or I'll talk through it and you observe. So our fuel is CO, and we're going to have some excess air. So I'm going to have a 1.45 in my mind. I'm doing this 1.45, kind of going right there, times whatever stoichiometric air. So air is oxygen plus 3.76 nitrogen. So you see why I have two spots left in front. One to get stoichiometric, then to put 145% theoretical air. Then we come over here and we're going to have some carbon dioxide. At this point, I can balance the carbon, and I can find that coefficient in front of the CO2s. That's a 1. Right? And then the next is H2O, and I can balance the hydrogens. Little different, isn't it? How many hydrogen are in my fuel? 0, so guess what the coefficient is in front of the water? 0. So it's a little different. It's like water doesn't go out. If you want, you can just get rid of it. There it is, gone. Now let's rebalance for the oxygen to get stoichiometric. So what is the coefficient I need to put right there in front? Okay, I'm going to pause because the people at the AM didn't do it very well. I said, does this coefficient is equal to 1, 2, or 3? And I had all of them. I got it wrong. You know what? I did a different fuel at the 9 o'clock. Didn't I say I changed my fuel? I changed my fuel. So it's 1/2, 2 halves, or 3 halves. Which one is it? 1/2. There you go. I forgot I changed my fuel. I had a different problem I solved this morning. Very good. You're more alert than I give you credit for. Now, what do? Is we multiply by 1.45 to have the 145%. And if you want, you can combine that. You can say that this coefficient right here is 0.725. Okay. And because we're only burning 100% of the stoichiometric, but we were fed 145%, so we have 45% left over of the oxygen. And so when we rebalance our oxygen, we're going to be 0.45 times 1/2 O2s. Or if you want, you can put this coefficient on the O2 to be 0.225. And then let's finish it out for the nitrogen. Sometimes it's nice to go ahead and multiply them out so that we just have one number in front of the nitrogen, 2.726. It's because we're going to use those n's, and we might as well just get them as a single number. Okay. Determine the air to fuel ratio for this. Should I let you do that? Or should I just do it and you watch? Air to fuel ratio, can you do it? So the air to fuel ratio is the mass of air, which is the number of moles of air, times the molar mass of air, divided by, this is for air, then the number of moles of fuel times the molar mass of the fuel, air and fuel. So we find out that we have 0.725 times 4.76. That's how many kilomoles of air come in. And its molar mass, 28.97. You divide by 1 right here. And you have 28.01. And the air to fuel ratio comes in at 3.57. Done. How about the exit temperature in Kelvin? How would you find, what's the strategy for the exit temperature in Kelvin? First law. And what type of, is the reactor insulated? What is the rate of heat transfer out of the reactor? Nothing. So what you could have rephrased this. What could they have asked you to calculate? The adiabatic flame temperature for this condition with excess air, with that fuel. That's what you're calculating. All right? So you go to the first law. Let me go ahead and, I don't know. Let me go ahead and write it. Q dot divided by N dot F, that's 0, minus W dot CV divided by N dot F, that's 0, equal to, then you have the sum of the stoichiometric coefficient times the enthalpy formation plus H bar, the exit temperature. That's our unknown. That's what we're trying to solve for. Minus H bar at the 298 Kelvin. And this is for each of the products, equal to the sum, not equal. Let's do plus. Minus sum of the reactants, the stoichiometric coefficient, enthalpy formation. Then we have plus the enthalpy temperature coming in, minus enthalpy 298. And I think I've written it correctly. So because everything comes in at 298, that's easy. We just have to have each of the reactants, so what we'll have is we'll have the N times enthalpy of formation for the carbon monoxide plus, but what's the enthalpy of formation of oxygen and nitrogen? 0. So that's the end of that. Okay. But we come over here and we have, let me put this equal to, switch it on the other side. Then I'm going to have for the products, we'll have N times enthalpy of formation plus the enthalpy at the temperature exit minus temperature or enthalpy, molar enthalpy 298. Oh man, this carbon dioxide, I didn't leave enough room. Then I have to do it for the oxygen and the nitrogen. True? So I have to do it for the oxygen and the nitrogen. And the enthalpy of formation will be gone, but the H bar 298. This is for the oxygen. Great, I need to scoot this down. And then we'll have plus N enthalpy at the exit temperature minus enthalpy at 298 for the nitrogen. True? Okay. Have you solved one of these by hand yet? You okay? How do you do it? Iteration. So you just have to guess and iterate. And in your numerical methods class, how many people remember root finding methods where you bracketed the root? You bracketed the root, right? And then you kind of moved in either from the top or the bottom. Same thing by hand. So I would grab a temperature that you think is pretty low It doesn't have to be ultra low, but just kind of lowish, in one that's a little highish. And when you don't know, grab one a little lower and a little higher to try and bracket it. But even if you don't bracket it, it's still decent because you can, if you have too low estimates, you can still extrapolate and you'll get there. It's just extrapolating outside of your bracket. Hopefully all of that makes sense. Okay, so let me do this. So I have to get a lot of data out of tables. So first of all, for the fuel, we have to get that enthalpy of formation. Boom. All right. And then for our water vapor, here's our column for our water vapor right here. Here is our enthalpy of formation of water vapor. And then for the nitrogen, 0, oxygen, 0, carbon dioxide, have an enthalpy of formation. So you know where you get your 3 enthalpies of formation. You need it for CO2, you need it for H2O, and you need it for CO, the fuel. Actually, right there is the fuel too. I didn't even need to go to this table, did I? Isn't that the same number? So, well, anyway, since CO is the fuel. Okay, now, we're always kind of referring back to 298. So we're going to need our enthalpy for our carbon dioxide at 298, but we don't know the exit temperature. You could guess 1200 and you could guess 2500. Do it for low estimate and then do it for high estimate. Same for the water, 1200 enthalpy, 2500 enthalpy. Why did I grab 12 and 25? I don't know. I'm just trying to bracket. And then the same with the nitrogen. And actually you have some excess oxygen, don't you, in the products. So you have to do that for the oxygen. Did I leave the oxygen out? No, I had the oxygen, nitrogen, carbon dioxide. What am I doing? There's no water. Get out of here. There you go. I fixed it. No water. Usually there is. Okay. So when I solved it, what I found was an imbalance in the equation when it was temperature was 1200. I found the Q over N fuel to be negative 155, 163 kilojoules per kilomole. With the 2500, I found it's 59,207. What do I desire? This is what I desire. That's what I want. I desire Q over N of F to be 0. Here it's like I'm solving for it, guessing and iterating on the exit temperature. And so then the exit temperature, just by this bracket method, comes in at, you just do a linear interpolation of 2141 Kelvin. Well, there's not a table with 2141 Kelvin. So you can take a look what's close, around 2150. And if you run this number again with these enthalpies, carbon dioxide, enthalpy of oxygen, enthalpy of the nitrogen, you will get very close that it'll be the adiabatic flame temperature of 2150 Kelvin. Good to 4 significant digits. If you want the 5th, well, it's not a 0. It's another number after that. But then you have to do interpolation. So, okay. So that's the answer to part C. How about part D? What's the amount of carbon dioxide in the products per kilogram of the fuel? So, can I give you a second to answer part D? It's a little easier. No iteration required. So this answer, what you have is the mass of the carbon dioxide per the mass of the fuel. And we have 1 kilomole, so you just multiply by the molar mass. 1 times the molar mass of carbon dioxide, 44.01 divided by. You have 1 fuel, and the fuel is 28.01. And so I didn't leave any room, did I? Okay, well, here. The answer without boxing it is 1.57. All right. Part E. Rate of entropy production in kilojoules per Kelvin per kilomole of the fuel. What are they asking us to calculate for the last part? Sigma dot divided by n dot fuel. So if I can maybe put it right in here, I'm calculating sigma dot per n dot of the fuel. This is the rate of entropy production per kilomole of the fuel, or kilomole per second. You know, it's a flow rate or a production rate over flow rate. The units on this are kilojoules per Kelvin kilomole of fuel. All right. So we look, how do we calculate that? Well, because it's adiabatic, is there any entropy transfer with the heat into or out of the control volume? Because it's adiabatic, that's 0, because Q dot 0. Okay. But then we also have our terms. We have a sum over all the products, the same stoichiometric coefficient, but we have the absolute entropy at the exiting temperature of the products minus, because it's all ideal gases, R bar, natural log. I'm just going to put YI for each of the products. The mole fractions, because the actual temperature divided by the reference temperature is the same, cancels, minus the sum over all the reactants, and S bar not absolute entropy incoming, minus R bar natural log of YI. Now, I have to be a little careful. When we had our reactor, was there a pure stream of carbon monoxide, of fuel, and then the air stream, and then they mixed in the combustion chamber? If so, then the Y of the CO in that stream, not CO2, but CO in that stream is 100%. And in the air, it's 0.21, and for oxygen, and for nitrogen, 0.79. But if they would have said this is already mixed and then it enters the combustion chamber, then I've got to go and get the balance. And so I would look back at my reaction equation right here, and I would say, let me try and write it over here. I would say I'm going to have 1 CO plus 0.725 oxygen plus 2.726 nitrogen, and then I would get the mole fraction for the carbon monoxide, which would be relatively high. It would be 1, I'm running out of room, aren't I? Yeah, the mole fraction of the carbon monoxide would be 1 divided by 1 plus 0.725 plus 2.726. And I don't remember what that is. But that's not our problem. It wasn't already mixed before it went in. It's coming in a pure stream and in pure air. Okay? Okay. So all of the information's here. We just have to get the absolute entropies of the incoming 298 for our fuel, carbon monoxide. Actually, that's also right up here, isn't it? Carbon monoxide at 298. That's the same number right there. And then we have to do it at the elevated temperature for our adiabatic flame temperature, 2150. We have to get the carbon dioxide, S bar naught. We have to get the oxygen, S bar naught, and the nitrogen absolute entropy at that elevated temperature. All right. You do have to calculate those mole fractions in the products. The mole fractions in the products, let me just kind of give you some numbers. We're going to have carbon dioxide is 253, 25.3% for the CO2. For the oxygen, it's 0.057, about a little less than 6%. And then for the nitrogen, it's 0.690, about 70%. That's right. Okay. The answer is that the entropy production per molar flow rate of the fuel comes in at 211 kilojoules per Kelvin kilomole. Make sense? So we're done with that. Sorry, let me put this back. Do you want to? Is that legible? With that, I'm going to go ahead and stop, and I have a survey for you to answer.